Thank you for the introduction. G'day, my name is Brendan, and I'm going to talk about using BPF Superpowers on Linux. As I was introduced, I work at Netflix. We have lots of Linux and also lots of FreeBSD. I'd like to start straight away, inspired by a talk I saw recently. Give me 15 minutes and I'll change your view of GDB, which was really good. And I thought if you give me 15 minutes, I might be able to change your view of Linux tracing. So I have a machine set up here. It has a very recent kernel. And I'm going to create a workload in one terminal where I'm pinging localhost. And now I'm going to do I should mention that I've actually got my noisy typewriter set up because I'm used to having this. I actually like having audio feedback when I type. I hope you enjoy it as much as I enjoy it, but we'll find out. So, it's great. You should try it. So, I'm going to start with a tool called funcount, and I'm going to trace all kernel functions that contain ICMP because I've created an ICMP workload. It's so satisfying when you hit enter. So while tracing, it's matched a bunch of kernel functions. Now, if you're new to this and you don't understand what the kernel functions are, that's fine. It's open source, so we can look it up quickly. So I have cscope set up on the source code in another window. Hands up if you use cscope. It's an old source code browser. If you use a different one, that's fine. So I can look up these definitions. I'm going to pick on, so at the bottom we had ICMP receive and then ICMP out count. Let's start with this one. So now it's looked it up in the Linux kernel source. I can see ICMP out count. It has a struct net, a type as an argument. It's bumping counters in SNMP. So I was counting them in the kernel, and I can actually add an interval so that I can see it every second. Okay. I can also use another tool. This is another tool I wrote where I will trace that function so I can see it being called. So I can see it's being called twice a second. And I can also see the on-CPU process, ping, timestamps, and other information. Now I'd like to see some of the arguments. So it had a net, a struct net, and also a type. Let's print out the type. So I can print that out. That's going to be in the register, SI register. I can give that a little alias to decorate the output. So type is 8 and 0. You might be wondering, how did I know it's in the SI register? It's because I've just done this far too much. But if you forget, you can look up in man syscall, which has the ABI for different processes. And down here, we've got x86-64. So I can see the first argument should be an RDI, the second argument should be an RSI, and so on. So the second argument was RSI. I'm printing it out, type 8. That's great. I believe type 8 and type 0, they're going to be ICMP echo request and reply, if I just look them up. So, okay, so here's ICMP echo reply. I just want to look at the table of macros. Ah, so good. 8 is echo request, 0 is echo reply, and that's what my quick one-liner is showing here. So we see the 8 and we see the 0 because I'm pinging localhost. Kprobe has a bunch of options, so I can do kprobe -s, and I can see the stack backtraces. This is great as, oh yeah, it also does sound effects for the mouse wheel. So type 8 was the echo request, and the kernel stack backtrace is coming out of sock send message, inet send message. So it's sending the request, and then when we do the reply, it's coming out of ICMP received. We process that, that's now ICMP echo, and away we go, we're pushing the ICMP echo reply. This stack's really interesting because it actually starts with since it's over localhost, the network stack folds in on itself. So you can see how we're doing the send message, we're going to IP output, we're going into the bottom half, we're doing the driver stuff, and then we receive it again because we're the same computer. And then we go back up into the receive path. So you get to see a send path and a receive path at the same time, just because I'm doing that over localhost. So that's great. So I've looked at counting it in kernel, and that's actually doing it efficiently. My func count is summarizing it in kernel, and then doing kprobe for dynamic tracing and printing out some events. I can do some other things to this as well. So I can do func graph. So well, it was ICMP out count. Func graph will trace the child calls that function makes. So that function, I can look at the stack backtrace, and that tells us how did I get there. The children calls will tell us what did it call next. So that one's actually kind of boring because it's not doing anything, but let me pick out on one of these other ones. ICMP receive. And it's doing lots of stuff, okay? And it's also giving me some microsecond timestamps. As a performance engineer, that's great. I can actually added some switches to this so I can limit how deep it will walk. So I can say func graph minus M2, and I can only see, that might be enough if I want to drill down and find the next level. There's another tool, func slower. I can do func slower, ICMP receive, and it takes an argument. It will tell me if function calls exceeded that argument in microseconds. So I could say, tell me if ICMP receive ever exceeds 5 microseconds, and it's only printing out those instances of that. That's pretty great. And I can do other things like, that's just ICMP. I picked it as a nice example this morning. Here's all of TCP. So there's lots of stuff in here. And you can imagine me picking any of these kernel functions and then looking up the source code, finding out some arguments are interesting, and I can manufacture my own tools on the fly to do any sort of deep analysis of the kernel. That's a little bit tricky if you're not doing kernel engineering all the time or this type of work all the time, which is why I create these front-end tools, things like exec snoop. So exec snoop in another window, if I type ls, and that's my ping command. It's tracing, it's doing something useful. It's just tracing which commands were executed and then printing out information. So I guess ls is alias to ls color equals auto. So I have a number of these commands. It seems like we can do quite a lot. We've got func count, func graph, latency. I can do kernel stack backtraces. I can look at arguments. Oh, there's one thing I didn't do, which was... So this was actually pretty easy, where I'm just picking off the first argument. But if I go back to ICMP out count, that was the second argument. The first argument is a struct net. So just to show you when things get a little bit more complicated, if I go to struct net, this time Cscope lets me down a little because it's not matching it directly. I have to find it. So, okay, there it is at the top. So here's struct net. I may be interested in a member from struct net. So, well, there's a lot of structs here, so I'd have to go from a member to a member and keep walking, but I want to pick something simple. Let's pick index. So if I figure out the offset in here, so remember I can go man syscall. I know that's going to be the first argument. It's going to be in RDI. I can do my kprobe. I can print out RDI. Okay, I don't need the stack backtraces this time. Okay, so there's a memory address. Now, if I happen to know the offset of what I'm after, I can type it in, like offset 32, and then dereference it that way. And I can be more, and I can say, well, that's actually an unsigned 8. But it's pretty hard to look at a very big struct and just know as a human where the offsets are. So I actually cheat this. I don't think this is documented anywhere. So I like to borrow another tool to do that for me. So I was going to go net, and then I was going to pick on, ifIndex. This is the perf command. This system has kernel debug info on, although I'm not using kernel debug info for any of the demos. I don't like to have it installed on my systems because it can consume gigabytes of space. I have one system at Netflix with kernel debug info on just so that I can run this one command. And what it does is it uses perf, and it pretends to instrument what you give it, and it tells you how it did it. So if perf probe minus n says don't do it, minus v for verbose, ICMP out count, give me the ifIndex member, and then it says, well, I would have got it from here. So I log into that one machine at Netflix, I run my perfprobe -mv, and then I can copy and paste that into my kprobe tool on all the production machines. And that tells me where the IF index would be. And that's how I do more complicated things by walking through members, is I just happen to have one system with kernel debug info. So that's a lot of demonstrations. Has anyone used FTrace before? Hands up if you've used FTrace. Oh, that's pretty good. We've got like maybe 10% of the people. Everything I've just demonstrated here is from FTrace. FTrace was added to the kernel in 2008. So it's been around for a long time. So nothing of that is new, although it might feel new if you haven't seen it before. And one of the problems in Linux tracing is we don't really have marketing or education. So we have all these cool features in the kernel, but people don't know about them. So that's FTrace, and we've had that for a long time. I wrote a bunch of tools, perf tools, that are shell script wrappers to FTrace. They're very simple. You can read them. They're like 100 lines each. They're very simple. Most of the work you saw, all the nice things like funcgraph, Stephen Restat, who's the author of FTrace, did all the hard work. So he got that going into the kernel. He's the engineer who's working on the real-time kernel, and he needed a very good suite of tools to do performance analysis. So I just put wrappers on it. But Stephen Restat did a lot of the hard work, and it's in the kernel, debug, tracing, it's this stuff. So you can turn on FTrace filters, and I can do kprobes and whatnot. Set up stack traces, do the function graph, and so on. That's FTrace. So going forward, now actually one more demo I did want to do was exec snoop. I was playing around this morning to look for some performance issues to show you how you could get value from these tools. And the first thing I noticed was when you logged into the system, there's a little pause. Even though I'm running this as a VBox virtual machine on my laptop, there's like a 100 millisecond pause from when I hit enter. And just by running exec snoop, I can see I found out what that was about. So it was calling this EDC update-motd.d stuff, which is new to me. And it turns out if I copy and paste this, the reason, so that's taking basically the 100 milliseconds. The reason why there's a little pause when I'm logging into my virtual machine was simply printing out the message of the day, since it's using this new stuff. So I was looking at that as the first demo to do, and it's like, actually, that was just one command. So I came up with ICMP to try instead. Now that's FTrace. I want to mention perf briefly as well. So perf started off doing things like this. Perf events started off as a performance monitoring counter tool, and it is great at looking at CPU cycles, instructions, IPC. It doesn't work on my virtual machine because it hasn't emulated the PMCs, but normally this would give you some output. Perf evolved, and it can do a lot more now. So it can do software events, it can do tracepoint events. These are static kernel tracepoints. And it can also access the user level probes as well, and so can FTrace to some degree. A big feature about perf is that FTrace was developed by Stephen Restat so that he could get his work done on the kernel. It wasn't really developed as a multi-user tool, and it's a little bit tricky to run multi-user. You can set it up with separate buffers, whereas perf was designed as the official tool so that multiple people can run it and to be very easy to use. And it supports a number of other things, like it can do user space stack backtraces, it can support additional symbol files, it can support different unwinding, libdwarf, and so on. I use it all the time for this. So just doing a profile. So profile at 99 Hertz, all CPUs, call graphs, sleep for 5 seconds, or 30 seconds or whatever. And that's taking time samples. And that time samples is another thing that FTrace doesn't currently do. And perf has all these things. I can report, so I can turn that into a report. Perf top will do this live, so I can see what's on CPU, consuming CPU live right now. So perf has lots of capabilities, trace points, stack traces, and so on. And I did do a couple of tools that wrapped perf as well as FTrace. But at this point, you might think we can probably do everything. Perf can do more user level and stack traces and symbol translation. FTrace can do a million things. What can't we do? So here's a tool. So I'm just going to drop caches and then. So IOSnoop prints out the disk I/O live and times it. And so it's telling me latency for each disk I/O and giving me some details. I wrote it a long time ago for Dtrace, and you find it on Mac OS X. That's great, but the way I had to implement it to do the latency timestamp is to pass it to user level and do the calculation there. And that's okay, maybe okay for disk I/O, which is not at a high frequency. Let's just do more. I/O latency is summarizing it as a histogram, but that summary has to be done in user level, so I'm passing every event to user level and doing the summarization there. That's not terribly efficient. It doesn't scale for things like scheduler events, and many times in the past I've analyzed scheduler bugs and looked at scheduler latency. And that's what FTrace and perf events haven't historically been able to do custom latency calculations in kernel, to do custom histograms in kernel, and to do more programmatic capabilities. That's what BPF lets us do. So with BPF, I now have a new suite of tools, and that's what I'm talking about in this session, and these tools can do in-kernel summaries. So I've got similar ones. Here's bio latency. So I'm now doing a histogram in microseconds of the disk I/O latency. Don't worry too much about these warnings. Someone should fix the... my BPF tools use kernel headers to figure out some things, and there is like a lint warning right now. Someone needs to fix it because it's annoying. It prints out whenever I run my tools. So now I can code these tools efficiently because they're using BPF. Basically the same tools. So here's BioSnoop that will do the same thing. So you can see it's now doing latency calculation all in kernel context. Instead of passing both the start and end and letting user space do the calculation, I can now summarize it there. I can also do things. ext4 slower is another favorite tool of mine. So I can say, show me just ext4 operations slower than 1 millisecond so that I can either exonerate the file system or show it had a problem. I can do TCP top, so going into TCP tracing. At the moment, I just have a couple of SSH sessions. It's not very interesting. And there's lots of stuff. TTY Watcher is another favorite one. I have another window down here. That's dev PTS2. And in this window, I will say TTY Snoop dev PTS2. And now in this window, whatever I type, it's showing it in the other window. So I'm able to attach to another TTY and then just print out the same characters, which is a little bit spooky. I did this before with a tool called Shell Snoop. You can actually attach my TTY Snoop to dev console, and you can actually watch console messages live. So BCC, BPF, it allows us to do the final things we need to do for advanced kernel tracing, to do in-kernel summaries. I've been porting a lot of my old tools over to it, and things are getting more efficient. BPF is designed to be production safe. So that was my quick demo. 2 years ago, I gave a talk on FTrace, and where I introduced the perf tools. Now I am giving the talk on BPF, where my FTrace perf tools, in some ways I knew BPF was coming, and these were a band-aid for older kernels because they work on 3. whatever, whereas with the BPF tools, you do need a 4 series Linux kernel. So at Netflix, we still have a lot of 3 series kernel running, and I can use my perf tools on that. This diagram is online, and I show whereabouts in the kernel these tools are instrumenting. So what dynamic tracing can do? Previously, tools were developed, like if you go back 20 years and look at Unix, tools were developed by the Unix vendors, and the source code was usually closed source. The metrics they exposed were often incomplete. And so those of us doing performance analysis got very good at the art of inference and making do, reading the tea leaves from the system metrics. In fact, that screenshot might look familiar, but I think I took that from Unix 7th edition on a PDP emulator. So some things haven't changed in a while. With dynamic tracing, we get crystal ball observability. Any kernel function, any user space function, I can trace it. Just like I was showing with cscope, I might walk arguments, I might look at latency, I might look at call graphs, and so on. I can come up with new tools. I can fill in all the gaps and missing pieces. I'll turn the sound off now. In Linux, there are many event sources that these tracing tools can consume. So there are trace points, which are static, and they're great to use because they don't change between kernel versions. But trace points aren't complete. There aren't trace points for everything. So dynamic tracing fills in the gaps. So there's uprobes for user space and kprobes for kernel. PMCs for doing low-level things for the CPUs, and so on. It's efficient. And just to highlight this, previously, if you say wanted to trace TCP retransmits, then a common technique would be to TCP dump to a file and then reread that file with an analyzer like Wireshark or Ethereal, and then figure out where those retransmits were happening. And there's a lot of overhead for that, especially if you're doing millions of packets per second on 10 gig Ethernet. So I'm taking send receive, I'm buffering. It has been optimized a lot. TCP dump has been optimized, but we still have to write it out to the file system and then disks and then reread it and then analyze it. With the new wave dynamic tracing, if I just wanted to see retransmits, I can put my finger on the TCP retransmit kernel function and say, just trace that. So I don't touch the send receive path, that goes at full speed, and I just pluck out the information that I want. It lets me do new CLI tools, which I demoed. Also, visualizations and GUIs. This was added in Linux 4.0 by Alexei Staritoyev, the lead developer of BPF, based on my earlier work with heat maps of storage, I/O, latency. And I had a paper published in Communications of the ACM a while ago because it's a very useful visualization, but we haven't seen widespread adoption yet, as doing the efficient aggregations in the Linux kernel has needed more programmatic capabilities. So now that BPF is coming in the 4th series, I hope this becomes more commonplace when you use performance tools. Heat maps are great because you get to see whether it's a multimodal distribution, you get to look at latency outliers, you get to see how that changes over time. So it's more than just a histogram. And we should see more visualizations and GUIs now that people can access so much more information from the kernel. How we intend to use it at Netflix is a self-service GUI. So that's an example of Vector, which we've open sourced. You click a button. At the moment, you can do flame graphs from Vector, CPU flame graphs using perf to sample, but we're now developing it so that it can make use of the new BPF stuff that's in the 4 series kernels. And that may be similar to how you might ultimately end up using BPF yourself. You may not go and hack away in the kernel source code like I did. You may end up being a consumer of a GUI product. You might use Vector once we open source it all. You may build your own, or you may also buy your own. And so I know there are some companies like, we don't use them, but companies like Seconis and Weaveworks, I believe, have done some initial BPF work to get some instrumentation in. And I'd expect more monitoring companies to pick that up as well. So if you think you may never use it at the command line like I did, that might be true. You might end up using it because you're a consumer of one of these tools. And we can measure everything. So I'm a big fan of performance analysis methodologies. So being able to look at why I'm waiting on locks, anytime I block a thread. I think CPU analysis is a pretty well-solved problem, although it is more complicated than it might look. We can always sample stacks, we can use PMCs. It's off CPU analysis and all the reasons why threads block that BPF allows us to attack more practically, because we can efficiently trace the scheduler, where before there was a lot of overhead with that. So introducing BPF, I have a Linux tracing timeline here, and it's been a long way coming. So there were prototype dynamic traces in the 90s. Linux actually had dynamic tracing in the year 2000. LTT integrated with Dprobes, an IBM project, but that was not integrated into the kernel. Kprobes came a little bit later. Some microsystems launched Dtrace in 2005 for Solaris, which was great as it was an awesome tool that proved that dynamic tracing was useful, and I used that quite a lot. Then we saw some projects like SystemTap and KTAP, and one of the large challenges of these other tools that were being developed was that they weren't being developed in tree. They were third-party tools that were being added on. However, the Linux kernel has slowly been getting those additional capabilities. FTrace was added, perf was added, tracepoints was added. FTrace and perf events have had many enhancements, and now BPF has been added to give us the final piece of programmatic traceability. So the kernel can now do everything we want it to do. BPF. BPF actually stands for Berkeley Packet Filter, and if you run tcp dump -d, it will print out some BPF assembly. BPF actually originates to make TCP dump filters processed efficiently because packet rates can be so high. So if I say TCP dump host is this and port is that, that can be compiled into this assembly that's then jittered and optimized, and then the kernel can run that as a filter. That is run by little virtual machine. And it's been enhanced in recent Linux so that BPF, instead of just being a packet filter, it can do more. So it can, there was a BPF syscall specifically added. It can attach to sockets, kprobes. It can do binary output, stack traces, trace points, and 4.9, which is not released yet, but will be on Sunday, profiling. And that was the last piece. If you try to use BPF, it depends what kernel you've got. So if you're on, say, Ubuntu 16.04, you can use a lot of the tools, but there's some tools that won't work. If you're on Ubuntu 16.10, then most of the tools will work, just as an example. And to re-emphasize, BPF is in Linux. So if you're running Linux, you will be getting BPF. It's a matter of time until you upgrade, until you have a kernel with it. So I mentioned earlier, the lead developer is Alexei Stoitoyev. He started at Plum Grid. He's now working on it at Facebook. And Facebook have other contributors as well. The enhancement started off for virtual networking. So a virtual network switch or router could be written in BPF. And instead of just filtering packets, it could redirect packets from one CPU to another and do things you want from a virtual switch or router. It has been we realized that it could be used for other things as well. So security, intrusion detection and enforcement, and programmatic tracing. There is a mascot. It's a ponycorn. That's because Dtrace has had a ponycorn mascot for a long time, which was created by Deirdre, who's here, who created both of them. BPF has different front ends. Like, you don't want to be writing it in BPF assembly. So you can write BPF programs in a front end called BCC, which I'll get into a lot. I'll mention the others. Briefly, how it works. The user space program is compiled into BPF bytecode. It's sent to the verifier in the kernel. If it passes, BPF can then be executed, and it can attach to kernel dynamic tracing, user space dynamic tracing, and trace points. And there are two ways it can provide output back to user space. Perf output for doing event-by-event information, and then maps for doing summary statistics, including histograms. Raw BPF looks like this. And there's an example in the Linux kernel, samples BPF sock example.c. I truncated 87 lines. It's really complicated. I've tried writing a raw BPF program from scratch. It is the only language that has so far defeated me. I've not been able to get it to compile. Anyone know what Intercal is? Intercal programming language? I guess some people. It's a joke programming language. I've successfully written a computer game in Intercal, which is included in the Intercal perf pit. And it's a terrible, terrible language on purpose. Raw BPF I found pretty hard. I think if I kept at it, I'd get it to compile. Fortunately, you don't need to. There is a C front end to it, which is also in the kernel source. There's a few examples of it, so that I can say, I'm going to kprobe this. Here's my program. It's very much C-like. Oh, actually, it is C, and it uses macros and things to work. And then there's BCC. It's a project created by Brendan Blanco from Plum Grid, and it's had a lot of help from Alexi and myself and others, including Sasha, Sasha and I gave a BPF tutorial 2 days ago here at LISA. And it has many tracing tools with it, and it provides a Python front end and a Lua front end. Now I can put an entire BCC program on one slide, a BPF program on one slide. On the left-hand side, that's the kernel side, which is in C. So it's saying kprobe block account IO completion. I define the arguments, and then I'm incrementing a BPF histogram called dist. And on the right-hand side is the Python that says, hey, I'm going to trace, and then sleep, and then print it out as a log2 histogram. So with BPF, we can now write programs that aren't in assembly that at least can fit on the slide, so that it makes things much easier to do. But it could get much easier than that, and tools like Dtrace have proved how much easier this can become. I'm not talking about it now, but somebody has tried a tool called Ply to be another alternate front end to BPF that just makes it trivial. So being able to do programs in a few lines. I've summarized the tracing landscape like this. So on the left axis is ease of use, and the x-axis is scope and capability. So things like Plime are very, very easy, although they're very early in development. You can see where BPF lives. It's easier than C BPF or raw BPF, which is brutal. Not as easy as things like System Tap or Dtrace, which are very easy. But it's very capable. In the slides, which I will put on SlideShare, I've summarized the state of BPF. It's exciting because the last feature we needed, profiling, so being able to attach to time samples, landed in Linux 4.9. And so it's currently 4.9 RC8, and it should cut on Sunday. So it can do everything. There's still some odds and ends that we need to look at. And you can also help out because BCC itself is on GitHub. But what we have now can accomplish the needs of advanced analysis and tracing. How to use it? At the moment, it's propagating into different repositories. So this is how to add it to Ubuntu Xenial. There is an install guide on the GitHub repository. And so we've now got it down to an apt-get install BCC tools. And Canonical are working on a snap so that it can be added as a snap as well. And I mentioned this earlier, but the newer the kernel you have, the better. You'll find more tools work. If you find some tools don't work, we've been putting older ones in the tools/old subdirectory. So you might find there's one that works for Linux 4.3, but the one in tools requires 4.7. I just want to mention this. If you look at BCC and you're doing performance analysis, I don't start there. I start using what the kernel gives me for free, those counters. And so I start with the regular things like uptime, dmessage, vmstat, mpstat, and so on. It's only after the basics will I be using these advanced tracing tools. I did do a tech blog on this on Netflix, performance analysis in 60 seconds, where I explained how I was interpreting all of those. So for a BCC checklist, now you can start with exec, snoop, OpenSnoop, ext4 slower or ZFS slower. There's a few variants in there. Bio latency, bio snoop. This would be the top 12 commands that I would run just to hit up low-hanging fruit for a broad look at observability. Now I demonstrated, I'll go through these quickly because my live demo didn't crash, it worked, which I expected. So I have slides showing some example output from the tool. OpenSnoop shows files that are open system-wide. If you use something like FTrace, the overheads of FTrace at the current implementation are very high. I would never run it in production unless I was desperate. Plus FTrace you can only attach to one process. So tools like OpenSnoop can trace open system-wide, which I find valuable. ext4 slower demonstrated, bio latency, bio snoop, cache stat for looking at the file system cache. There's a few TCP tools so far, and we'll be adding lots more. tcpconnect, just so that I can see who am I connecting to. And it's only tracing that path, so I don't pay a tax of send-receive tracing, except for the other way around. TCP retransmit, I had this tool done for FTrace, but I've done it for BCC as well. It's valuable in that it can also pluck out kernel state that you don't see on the wire. So I can say, well, the state of that session was established. Sometimes you get things like the last few packets in the fin sequence getting retransmitted. It doesn't really matter. But if it's during an established, that's more information that you might want to know. If it's during SYN sent, that's information you might need to know because you might have hit a backlog. There's examples of user space tracing like get host latency that instruments the resolver library. Run queue latency for scheduler analysis, and then profile, which is the last tool that only works on 4.9, so we can do profiling, time sampling. And also in Linux 4.9, you can do PMCs as well. There are lots of other tools in BCC that we're adding. There's single purpose and multi-purpose tools. Just to give you an idea of the multi-purpose tools, Sasha Goldstein wrote the next two who helped with the tutorial. Trace, it has this syntax that he's come up with. So you can say, I want to trace sysread only if arg3 is greater than 20,000. And then this is like a printf statement, print arg3 in that format. And it can do user level stuff as well. In the slides, I've got lots of one-liners that you can use with trace. It's fairly powerful. You can do trace points in user space and kernel, stack traces. And then there's a companion called argdist. So if I don't want to see per event output, I want to summarize something as a histogram or a frequency count, I can say argdist. And so that example is doing a TCP cleanup RBUF. I want to know this argument as a histogram. And so instead of having to write an entire BCC BPF tool, this one liner can do it for me. And that's summarized in kernel. There's lots of examples of that. That's using it at the command line, but I get the feeling not a lot of us will be using it at the command line. How many people use Dtrace at the command line? That's pretty good. So we must have like 10 people. A lot of people will use it from, we hope will be using it from GUI since it's part of Linux. So latency heat maps, again, at Netflix, Vector will be putting it into there, but you might consume it. You might build your own tool, or you might be buying a tool that has this. CPU and off-CPU flame graphs actually get more practical because they can be done efficiently. So CPU samples and can be frequency counted in kernel context. Off-CPU was fairly impractical before because it requires tracing all scheduler events, but that can now be aggregated in kernel context. So suddenly we can do new things with off-CPU analysis. That's the complement of the CPU flame graphs. Who's used flame graphs? Hey, so that's pretty good, like 20 people. Flame graphs are a great visualization for navigating sampled stack traces quickly. But we'll now be using them for other things, tracing stack traces. And things I'm starting to do is off-wake flame graphs where I have a blocked stack trace and I associate it in kernel context with the woken stack trace. I could not do this with any tracer before. BPF is the first tool that can do that association in kernel context so that I can see who woke up who, which is often required. And if I keep walking the waker stacks, I'll end up on metal. I call that a chain graph, where you can see every single stack from a hardware timer or interrupt that woke up my blocked application. This is just an overview for tool developers. I don't actually think many of us will do this, but I've got it in the slide so you have a taste of what it looks like. So all the event sources I showed before here, I've decorated it with which Linux version these appeared in. So the PMCs is Linux 4.9, that's the newest stuff. Quite a lot was in 4.4. My methodology is to start with a functional diagram and then to apply performance methods like workload characterization, latency analysis, and the use method. This functional diagram could be the kernel, your application, a distributed system. It gives you a starting point to iterate over. And it also forces you to ask questions that you want answered, and you then develop tools to answer them, instead of starting with metrics and then looking for an answer to your numbers. So bytehist prints the I/O size as a histogram. That's how it's implemented. And I've got a sequence diagram of how it gets loaded, but I've decorated the code here. So there's the C program and the Python program. I declare a map for the histogram, and then I end up printing it out. There are complications if you do this. BCC is getting better over time, but I'll admit it is quite hard. I've been porting over some Dtrace tools, and the BCC equivalents maybe 10 times as many lines and take quite a lot longer to write. At least it's doable, and that's a huge milestone for Linux. At least I can do my advanced analysis now and do everything I want to do, even though right now it's quite difficult. But fortunately, companies like Netflix, only a few of us on the OS team need to write the tools and then share them with everyone else. So there are some complications right now. If you want to get into it, there are tutorials. I wrote an end-user tutorial, a developer tutorial, and a reference guide. And I should mention there's also a Lua interface if you prefer Lua. So in summary, there's the tool diagram is on iovisor/bcc that shows the current tools and what they instrument. You need to be aware of which Linux version you're on. How many people are on Linux 4. something? Wow, that's so good. Thank goodness. I was wondering if no one would actually use this stuff for a year or two. Thank goodness you can use some of this. Hands up if you're on 4.4 or newer. All right, that's pretty good. So 4.4, a lot of the tools start to work. So, and once you're on 4.9, everything works. So that's really exciting. In the future, we'll be doing more tooling, bug fixes, better errors, visualizations, and GUIs. A high-level language might happen as well. We'll see. In the slides, I'll put them on SlideShare. I've got references. And that's my talk. Thank you. And before you run away, I do have some stickers down the front of the BPF Ponycorn if you'd like a BPF Pony sticker. So Deirdre has them down the front.
So the question I have is that do you see that we affect the performance of the system by the observation of the performance? Can we do that? Or is that something we'd prefer to minimize? And also, have you screamed at any disk arrays recently?
I have not screamed at disk arrays recently. Has anyone seen my shouting at JBods video? Okay, half the people, that's good. I was actually demonstrating Dtrace, and I was demonstrating a heat map, and I was showing how disk vibration could cause latency. Nowadays it's Flash, so I can scream really loud until I can dissolve the server in ashes. I don't think I'm able to break them. You mentioned the observer effect. It's very real. As a performance engineer, I have a very good gut for what I'm allowed to do and what I'm not allowed to do. And it's the big thing about BPF is it moves the threshold of what's possible. So previously, things like doing scheduler tracing and per packet tracing, it just hurts to do it through perf because I have to pass everything to user level. Now those goalposts have moved, so I'm allowed to do more of that now. But it's still ultimately everything you touch, you're adding cycles. And if you're doing something that's over 1 million a second, BPF can hurt. So what you have to think about is what is the frequency of the event. And tools like FuncCount will show you, if you don't know, will show you the frequency. So I should do a blog post of this is how my gut tells me scheduler events are frequent. Per packet is frequent. Block I/O, not so much, not too bad. Per process, process execution, not so bad. But I have a lot of those from experience. So I'm always thinking about the frequency before I trace something. And if you're unsure, you can always test it out. Other questions?